Okay, so we got that recording. I'm sending out the attendance sheet, so please sign it when you get a chance before the session's over. That'd be great. Okay, so the first thing you guys wanted to go over was Grignard reactions and what happens when you have an acidic hydrogen. So I'm actually going to draw out two examples for this, and we're going to go over like two different possible ways that you could answer that kind of question. So let's say we have a regular old ketone, and let's say we have something like this, right? So if we were given something like this, this would just be a normal Grignard reaction, right? And we can go ahead and first, we know that this part is not really attached, so our Grignard reagent looks like so. And so all we're going to do is add that reagent to the carbonyl carbon. And so since we don't have any leaving groups present, how many times can we do the Grignard reaction? 1, exactly. So we go ahead and form a tertiary alcohol, and we add our Grignard. Now let's say we have something like so. We have a carboxylic acid, and let's have the same Grignard reagent and H2O. In this case, we have an acidic hydrogen here, so a Grignard reaction cannot happen. But you had already said this in your original question, but what kind of reaction is going to happen instead of acid-base? I want everyone else to think about it. So if we have an acidic hydrogen and a super strong negative charge that can either work as a nucleophile or a base, what kind of reaction do we think is going to happen instead of the Grignard reaction? Not necessarily SN2. It's just mostly going to be acid-base chemistry, correct? So what we mean by that is this will steal a hydrogen and give those electrons here, and we would get this and this, right? So why do we bother, or I guess I should say, why would we say this is no reaction instead of showing this acid-base chemistry? There's two reasons, really. Why do you guys think we consider this no reaction when we're talking about the Grignard? Yes, exactly. So one reason is this is going to be a, whoa, I don't know what just happened. This is going to be a reversible reaction. It's going to be at equilibrium, and we're going to be able to go back. Ooh, sorry, my iPad doesn't want to function today. We're going to go back and forth all the time. So that's one reason. And another reason is actually because we're not talking about acid-base chemistry, right? So we're specifically talking about the Grignard reagent. So we want to do the Grignard reaction. So when he asks you to react this with a Grignard reagent, you are not undergoing the Grignard reaction. Therefore, there is no reaction. So that's why we would consider this one no reaction. Does that make a little bit more sense what the distinction there would be? I don't know why there's a random thing there. Yes? Okay, cool. The other example that I want to go over for Grignards, though, is what if we have something like, ooh, this is a good one. Sorry, I just want to make up a really good reaction, and I can't talk and write it at the same time. And yes, so someone asked a question about like what can react as a Grignard reagent, what can't. I do have some practice problems for that, so we can go through that in a second. I just want to have this reaction real quick. So yes, okay. So this is a multi-step reaction where we start out with an alcohol and we have SOCl5. Do y'all remember what SOCl5 does? It turns OH to yes, OH to chlorine, and that's because SOCl5 works exactly the same way PBr3 does. It just replaces a chlorine instead of a bromine. Awesome. And so magnesium is going to turn what to what? This one's a little bit less straightforward, but I believe in you guys. Let's see if you can get it. So once we turn OH to chlorine, what will the magnesium do? So someone said OH to Mg. That's a good guess, but not exactly. Because remember, at this point, we have a chlorine here instead of an OH. So adjust your answer just a tiny bit. And yes, it would go from Cl to MgCl. And so that means we made what now? If we have MgCl or MgBr or anything like that, what reagent have we made? The Grignard reagent. Awesome. So the reason I show it to you like this is because it's a lot quicker when you're on the exam instead of drawing out every single step. So we went from this alcohol to this Grignard reagent. So this is B. And then we're going to react that with this thing right here. So this carbonyl has one leaving group. So how many times are we going to add the Grignard reagent if we have one leaving group present? And I'll zoom out so you guys can see it. If we had 0 leaving groups present, we did it 1 time. So exactly, we're going to do it 2 times. So let's go through and number our carbons. So we know we have a 5-carbon chain. 2, 3, 4, 5. So just for reference, that's 1 and that's 5. So on carbon number 1, we form an OH. What do we have on carbon 5? What substituent do we have on carbon number 5? OH, perfect. And so then on carbon 1, you guys told me we are also going to do this reaction 2 times. So we have the Grignard added twice. And the Grignard has 1, 2, 3, 4 carbons, and we attach at carbon 2. Ta-da! So this is our final answer. Any questions here? Be happy so far? And yes, exactly. So technically, okay, wait, let me read the question first. So the question is, if this was a reduction reaction, the sec butyls would be replaced with hydrogens, right? So yes, exactly. Technically, this is a type of reduction, because this carbonyl is being reduced. But if we were doing just a regular old plain reduction with LiAlH4, we would replace the alkyl groups with hydrogens. You are absolutely correct. I'm so glad you made that connection. All right, so let's move into this. So Katrina and I worked on this. It's a big boy. It is a huge thing of practice problem. Come on, dude. Ugh, okay, I'm struggling to make this work properly. There we go. All right, so let's go to chapter 13, and I am looking for some good examples of the questions you guys asked. Bless you. No, that's not it. Grignards were chapter 12 or 13? I think they were 12. They were 12. So why? Where in the world is it? I know I'm not crazy. He had a bunch of practice problems like this. So give me 1 second to find it. And if I can't find it, we'll just do the rules like verbally. For some reason, it's not here, so it's fine. So essentially, the Grignard reaction is not going to happen when you have any kind of acidic hydrogen. So things that are considered acidic hydrogens are carboxylic acids, triple bonds, and heteroatoms such as OH, NH, and SH. So if you have any of these hydrogens present on your molecule, the Grignard reaction will not happen. In any other case, you can perform the Grignard reaction. So if we are talking about making the Grignard reagent, you want to have an alkyl halide with nothing else on the chain. So like if we're making the Grignard reagent, we want something simple and straightforward that looks like this. Or like this, any kind of halogen. And you want it to be as the least sterically hindered as possible. So you would prefer this over this over this. They can all still happen. What couldn't happen is, let's say we had something like that. So this cannot be turned into a Grignard reagent. Same is true if you have a double bond. Same is true if you have a triple bond, a carboxylic acid, an OH, an NH, or an SH. Sorry for the little stutter and like word vomit, but does this sort of kind of make sense? Does it answer your question? I wish I could have found a good example. Yes, okay, cool. You're very welcome. All right, so yeah, right? Like, I know one exists. I just don't know where it went. It's weird. But, okay, so someone had asked about the hydrolysis. I'm trying to find what exactly the question was. So, hydrolysis, hydration, dehydration, all those kind of things. So, let's actually go here. And, okay, so as far as dehydration goes, you want to think of these two. So, with H2SO4, we know that in general, H2SO4 likes to do elimination. Plus, we add heat, so that means a dehydration. If we have POCl3 and nothing else, we can also perform a dehydration. That's a little bit less common because POCl3 can do a bajillion different things, so it's hard to tell like when you're just doing a dehydration. So usually he will ask for H2SO4 in water and heat. And in that case, you will get this answer. And let me actually make a new page so we can put them all on one page. So if we have an alcohol such as this one, and we have H2SO4, H2O, heat, we are going to do a dehydration, which means we get rid of the alcohol, and we get that. The opposite of that would be if we had, for example, this double bond. And what do you think we could use as a reagent in order to hydrate this double bond? Oh, yes, H2O, exactly. So we are going to use water, and that water is essentially going to be added back to here. And so there were some rules in Orgo 1 about which side you would add the OH and which side you would add the hydrogen. Does anyone remember that? If not, it's cool. But do you guys remember where you would add the OH? Yes, exactly. So the more substituted side you would add the OH to, the less substituted side you would add the hydrogen to. Exactly. And let's call this a hydration. There are also a couple reactions that I gave you guys, like the oxymercuration, demercuration, and bromination or something. Look those over like once or twice. Just make sure you have a general idea of what it is. I don't really think he'll ask you about it, but it's fair game because he went over it. And that's just another way we go from double bond to adding an OH. That's why I mention it. And let me just look at your question. Yes, okay, hydrolysis. So hydrolysis can kind of refer to a couple different things, but in this semester, we're talking about, let's say, we have something like this, right? And you're very welcome. Yes, take a break, grab a snack, take a nap, something before the review, get some relaxation time in there. Okay, so when we have a carboxylic acid derivative and we react it with NaOH and let's say water, we can go ahead and substitute the leaving group for our OH, and we call this a hydrolysis. So it's mostly about kind of having an idea of what you're starting with and what your reagent is going to do. So if you're starting with an alcohol and you have heat and H2SO4, that kind of stuff, you know it's going to be an elimination. If you start with a double bond and you have like some kind of H2O or acid or something, you know you're going to add something back to the double bond. So you're going to do a hydration. If we start off with a carboxylic acid derivative, you know that it's probably going to be either some kind of reduction or it's going to be a nucleophilic acyl substitution. In this case, since we have NaOH, we know that it'll be a substitution reaction, and we end up making a carboxylic acid, and that would be called a hydrolysis. Does that make a little bit more sense? So H3O plus, what does H3O plus on its own do? That depends on what the starting material is. So H3O plus could also do this. Theoretically, H3O plus could also do this, but it's less likely. I mean, it could. H3O plus by itself could also do a hydrolysis. So it really depends on your starting material. You're welcome. Okay. So I believe I covered all the things that you guys had already mentioned in the chat. So what else do you guys want to go over? I have that list of practice problems that I talked about yesterday for anyone that was here. So if you don't have like any specific questions, we can go through that or whatever you guys want. I'll give you all a second. Okay, so one person said practice problem sounds good. Does that sound okay with everyone? Yes, okay, cool. Where did she go? There we go. All right, so this packet starts with chapter 9, Are you guys cool starting there, or do you want to jump to like 11 or 12? Nine is good? Okay, cool. So, let's say we have something like this. Ew, I hate condensed formula, so I'm going to go ahead and write it out. You know what, before I write it out, we see two oxygens here, right? What functional group are those going to be? Excuse me. So what functional groups do we have present here? Yes, we have ethers. So if we have something that looks like so, two carbons on either side of an oxygen, we are going to have, let me just make sure I have the right number. Cool. We are going to have two ethers. So when we're looking for the number of signals, what is the first thing we're going to do? Starts with an S. We look for symmetry, exactly. So right down the middle, we see that we have symmetry here. And so symmetry means that the corresponding carbons on both sides of our line of symmetry are going to be the same, right? So this carbon and this carbon are the same. This carbon and this carbon are the same. So how many hydrogen NMR peaks do we have? Two, perfect. And how many carbon NMR peaks would we have? Two, exactly. So they would be the same. Perfect. So we like two. Let's say, no. Let's say we're doing this one. And here he's almost kind of mean because he doesn't point to which carbon he wants. He just says carbon 1. So let's say we have A, B, C, D. Which one of those would we count as carbon 1? A, yes. And why would we start counting up here at A instead of down here at D? I'll give you a second to write your response while I draw these out. Yes, so we have the substituents, or we have the greatest number of substituents on lower numbered carbons. Exactly. Cool. So these blue hydrogens that I have drawn out are both going to be the same signal. So we have internal symmetry here and here. So all these blue hydrogens are part of the same signal. So we're going to see if anything is within 3 bond lengths of those hydrogens. So 1, 2, 3, nope. 3, nope. So if there's no neighbors, we can call this what? Is it going to be a singlet, doublet, quartet, septet, octet? A singlet. Yes, I would agree. Does this molecule have anything higher than a singlet? What do you think? Are any of the hydrogen signals here higher than a singlet? Ooh, okay, so someone said yes, there's a doublet, so let's look here. So we have all of these that are the same, all of these that are the same. And the difference here, the reason that's different than the blue hydrogens is we have one hydrogen right here in the middle. So the purple ones have 1, 2, 3. They have one neighbor. And the red hydrogen is coupled to all of the purple hydrogens. So how many neighbors does the red hydrogen have? How many neighbors does the red hydrogen have? 6, exactly. So 6 plus 1 is a septet. Or we can just call it a multiplet. Good? Does all the stuff we just went over make sense? Yes? Okay, sweet. So next up, we have this one. So we're pointing at a hydrogen that's on the ether. So first thing is first, can we split through a heteroatom? No. So as far as lecture goes, we are not going to split through the heteroatom. Lab is a little bit different, but you'll deal with that when you get there. So, if we cannot have any neighbors, we can't split through a heteroatom. What does this signal have to be when we're talking about splitting and multiplicity? Yes, it has to be a singlet. So we can automatically get rid of all the answer choices that are not singlet. And now when it asks ppm, what is it asking for? Which one of the 4 main aspects are we looking at? Yes, this part is pretty tricky. But before we even get into the numbers, so what is this asking you for when it says ppm? What do you have to look at? We know the 4 main aspects are number of signals, splitting and multiplicity, chemical shift, and integration. So which one of those has to deal with ppm? Chemical shift, exactly. So when we look at chemical shift, we have to remember those regions, right? So we had the alkyl region. We had what? What comes after the alkyl region? And if you guys need a hint, let me pull up some notes from an earlier chapter. Do you remember this lovely chart that we made? So we have alkyl, which is 1 to 2.5. We have heteroatom. Does anyone remember where heteroatom goes from? It's 3 to 5. Yes, perfect. Double bond. Everyone forgets this one. Do you guys remember? It's 5 to say 7. And then aromatic. We skip a number for aromatic. We start at 9. So it's approximately, or just, darn it, it's approximately 8 to 9 ppm. Or in this class, I believe we say 8 to 10. And then, or no, I think we do say 9. Sorry. Around that region. Once you get to lab, those numbers shift a little bit. But for lecture, we'll say 8 to 9. And then the carbonyl region is from 9 to 12. So when we're looking at the hydrogen that's attached to the carbon that's attached to the oxygen, which one of these regions is it going to be in? Exactly. Oh, excuse me. It will be in the heteroatom region because we know things in the heteroatom region include hydrogens directly attached or hydrogens that are adjacent. And someone went further to say that this will be closer to 3 than 5 because of the oxygen. So that is correct. And I'm going to just tweak that a little bit. So when we're talking about the heteroatom region, we have 3 over here, 4, and 5 over here, let's say, right? So a 3 is going to be a nitrogen, a 4 is going to be an oxygen, and a 5 is going to be like a fluorine, right? And we can go higher or lower on this scale depending on if we are directly attached to the oxygen or if we are 1 carbon away. So automatically we can get rid of A because 1.0, that's in a different region. But we can choose from 3.4 or 4.5. So let's go back up to this like little number line here. If the baseline for an oxygen is a 4, do we think the hydrogen attached to a carbon attached to an oxygen is going to be higher than 4, or do we think it'll be lower than 4? Lower, exactly, because it's not directly attached, so it's going to be less de-shielded. Perfect. So we are going to say that the 3.4 answer is correct, and we would be right. I know there's a lot of zooming in and out. I'm sorry if that bothered anyone. But does this make sense? I know it's kind of tricky once we get into these little details, but hopefully once we did it that way, it makes more sense. Good. Okay, cool. So I'll leave this up for a couple seconds. I'll take a sip of my drink, and then we can move on. All right, so let's do a really similar one. So we are now pointing to a hydrogen that is next to a ketone, right? So does this hydrogen have any neighbors? No, because there's nothing within 3 bond lengths. So it has to be a what? Singlet. Sweet. So let's get rid of quartet and triplet. So between A, B, and C, or A, B, and D, we have to figure out the chemical shift, right? And if we scroll up a little bit, we can see these regions. So what region is a hydrogen next to a ketone going to fall in? Alkyl, exactly. So a lot of people put this in the carbonyl region, but it would be in the alkyl region because it's attached to the hydrogen next to the carbonyl. Exactly. So we know that the alkyl region is approximately 1 to 2.5 ppm. So this regular old ketone, do we think it's going to be closer to 1 or closer to 2.5? What do you guys think? Would it be closer to 1? Yes, it will be closer to 2.5. So something that would be closer to a 1 would be like a regular old carbon chain. A 2.5 would be a ketone. So for that reason, we're going to go with B. But let's say we had like a ketone that had like an OH over here or something. Now when we look at this hydrogen, what number-ish do you think it might be? Do you think it's still going to be 2.5, a little bit higher, a little bit lower? Ow. Don't mind that, I just kicked my desk. Yeah, so it would be 2.5-ish, but I would say it would be more like 2.5 to 3 because it's going to be a little bit higher than a regular ketone because it has this extra deshielded stuff going on. So usually when you see a ketone, it's like that 2.5-ish area. If there's a bunch of other stuff going on, like halogens, this, that, it's possible to go a little bit above 2.5. And I forgot to reveal the answer, but we were correct. Yay! All right, so it's 12:48, and I do have to close this meeting at 12:50 so that I can open up the next session. But do you guys have any questions, comments, concerns, anything? I'll send out the attendance one more time. Are a lot of you guys going to go on to the next session, or because I want to survive? You're not. And yes, you can definitely unmute to ask.
Hi Rosemary. I just have it's like a really weird question. Like I don't even know if I'm gonna be.
There we go. Now I can hear you.
Oh, hi. I just have it's kind of like a weird question, so I don't know if I'm gonna be like wording it right. But like, oh, I think the last SI session or the two SI sessions ago, you talked about like on an ether or like an epoxide when there's no catalyst, you like attack on the less substituted side.
Yes.
But when he's giving it to us in like a reaction, like a multi-step reaction mechanism with the arrows and everything, like how do I know if the H3O plus or whatever is a catalyst or it's just like the protonation step? Like how does that look in that arrow mechanism?
That is a great question. Okay, so, and I know exactly what you're talking about too, but let's say we have like multi-step, blah, 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 and at this point you have your epoxide. That's not an epoxide. Let's say you have something like this, right? If we have one arrow with the epoxide and then another arrow with H3O plus, that means it's not acid catalyzed. It's just going to be this in one step, and then once this is done, then we add acid just to do the protonation. If he were to give you just like this, then it would be acid catalyzed. If he gave you, what am I doing? This, and he did this, that would mean they're two separate steps, so it's not acid catalyzed. So these are the three ways he could kind of do that. So in these two, it's not acid catalyzed. In this case, it is acid catalyzed. You are very welcome. I hope this sort of kind of makes sense now. Orgo is really annoying just because they can ask you the same thing in a bajillion different ways. So I will see you guys in a little bit. Bye-bye.